Hello there, ladies and gentlemen. Welcome back to the Ephemeris Podcast, your weekly astronomy podcast. I'm your host, Aphelion, and thank you for joining me on the 8th episode of the 3rd season and the new chapter. As we are into the 8th episode at this point, I'm not going to go over the structure time and time again. It's 3 articles every week. The 3 articles that we have today are about a record-breaking quasar, the bipolar jets of a microquasar, as a nice segue from the first article, and then a bit of a different direction we're taking with the 3rd article. We're going to be talking about satellite interference with astronomy. So, without further ado, let's get into our stories this week. So, record-breaking quasar. We've talked about quasars before. They are accretion-powered supermassive black holes, also known as active galactic nuclei. They contain bipolar jets with strong plasma emissions, or rather, I should say, radio emissions. And we now know that quasars are the center of young galaxies. If not quite confirmed, then at least we can say that there is a fairly accurate correlation between quasars and galaxy formation at this point. So, yeah, we talked about that in the first season a little bit, but if you didn't know, now you know. So the new thing we've discovered about quasars that we haven't already talked about is the limit to how bright they can get and how fast they can grow. In other words, and in fact, we found the most luminous object in the universe in a quasar named J05294351. Again, I'm not a big fan of those numbered names, but the names are the names, so that is the name of the quasar that we've now found to be the most luminous in our entire universe. We've also found that this quasar grows by 1 solar mass a day, and that is extreme, to say the least. To put that into context, the mass of Sagittarius A star, which is the black hole at the galactic center, is 4.3 million solar masses. The quasar, J05294351, adds on Sagittarius A star's worth of mass in about 12,000 years. That is an extremely fast growth rate in terms of astronomy. And in terms of the mass that it already has, that's 17 billion suns. That is more than 1% the mass of the Milky Way in such a concentrated point in space that is a supermassive black hole. So I tell you what, these are some incredible numbers that we're seeing with this quasar here. It is huge. The quasar is 12 billion light years away, which makes it, part of a category of celestial objects that tells us more about the early universe and allows us to observe it in action. But there's an even crazier number for you all to digest that I'm going to tell you right now. The quasar is 500 trillion times brighter than the sun. Let's be honest. Face value, on its face, you're not going to be able to comprehend what 500 trillion is really like, because that's just too huge of a number for you to understand it as it is. But if I put it into context and tell you that your body has approximately 35 trillion cells, and comparing this quasar to the sun is like comparing a single cell in the human body to 14 complete human bodies, maybe that gives you a better idea of how big a number 500 trillion is. This quasar being 500 trillion times brighter than the sun is like, if you compare it to the sun, is like comparing a cell to 14 complete human bodies. That is absurd, and I don't think I'll ever be thinking about 500 trillion as a number in the same way ever again, because I was like, 500 trillion, what could you even make that equivalent to? And that's the best comparison I could find. So yeah, 500 trillion times brighter than the sun is really bright. You might be thinking how this is even possible, because it's true. I mean, these are some unfathomable numbers. Um, so, as we talked about, quasars power their black holes with accretion disks. And the accretion disk in this quasar has a diameter of 7 light years. That makes it the largest accretion disk in the universe. And just to make 7 light years sound like a huge number, it's the equivalent of traveling between the sun and Earth 443,000 times. So that is a huge distance. Again, like, I'm probably going to say huge a ton of times throughout this story here, but yeah, I mean, it's such a crazy object, and its discovery is even quite unusual because it's been in our sights since 1980, and the reason it's been difficult to spot this object as a quasar is because we observe it among a crowd of other distant objects. And the process of deciphering a quasar like this is usually done through automation and machine learning, but the machine can obviously fall short when it comes to observing some of these quasars as they are, instead of, like, say, just a really bright star. So that's the reason why we weren't actually able to figure out that J05294351 was a quasar. So yeah, it's sort of like a chess engine failing to see a path to checkmate in certain situations, like the way that it scans different lines. It's like it won't go too deep into a certain line because it doesn't give an immediate advantage. That's kind of analogous to what's going on here with machine learning not being able to detect our quasar that we're talking about here. So yeah, I digress. Yeah, that's pretty much all I have to say about this humongous and very, very luminous quasar. It is quite mind-boggling, and hopefully it seems like that to y'all too. So that is our first story about this incredible object. And our second story is going to be a nice segue, because we're going to be talking about microquasars and discovering their jets of gamma ray emissions. The difference between a microquasar and a quasar is that a microquasar is a smaller, compact region of space surrounding a stellar black hole rather than a supermassive one. And the jets in the microquasar that we're looking at specifically today, its speeds are close to a quarter of the speed of light, which is lightning fast. Figuratively, not literally. The particle acceleration conducted by this quasar is thus highly efficient as well. So what do we know about the object that makes this possible? Well, we know it's a binary system called SS433 or 433. It contains a A-type supergiant, and a stellar mass black hole. And the stellar mass black hole with its bipolar jets only extend over a small distance, about 1/10 of a parsec. But because the jets get amplified at a certain distance, we're still able to observe them, because 0.1 parsecs in terms of being able to observe objects that are like tens of billions of light years away is extremely small, and makes it very difficult for us to observe the object if we don't have it amplified in some sort of way. So the reason for particle acceleration occurring that will allow for this amplification we're talking about, that process is a bit complex, so just stick with me here. The explanation goes as follows. About 25 light years away from the black hole, there is a steep transition in the properties of the interstellar medium due to X-ray and gamma ray sources. And this leads to electrons being accelerated to points of extremely high energy. And when an electron collides with a gamma particle, it creates a gamma ray photon that is observable to us. So that process happening in in a large amount will create the amplification that we're talking about that will be able to, or will allow us to observe SS 433, which is our microquasar we're talking about here. So the significant part about this whole process that goes on is simply that the mechanism through which these particles are accelerated was poorly understood for years, and now that we understand this phenomena here, we now know more unique ways in which some of the most powerful emissions in the universe originate, because as has been inferred from previous episodes, gamma ray bursts are important, and gamma ray emissions, X-ray emissions, UV emissions that are coming from these huge stellar objects are important to us. And if we can discover new ways in which they appear in our universe, then that's, better to our understanding of what's out there in the cosmos. So yeah, that is our short little story on a microquasar that had some unusual properties with the way that it emitted its bipolar jets, essentially. So with that, it's time to move on to our third story, which, as I said, will move in a slightly different direction from our previous articles. We usually cover discoveries in astronomy and new developments with celestial objects, but this article is going to be more on the political side of the field. It's going to be about the UN, and one of its committees addressing satellite interference with astronomy. Satellite interference with astronomy has been a contentious issue in the field for as long as I can remember, and probably was an issue before I even got into astronomy itself and kind of studying it. But the sort of what happens with satellites being in Earth's low orbit is that it creates trails in astronomical imaging if you're looking in like visual wavelengths, and it also creates strong signals that ruin radio observations. So that's where the interference comes in with satellites that are in Earth's low orbit. They come from, like Starlink mega-constellations and those type of satellites that are in our orbit. And so, yeah, in that way, satellites tend to be a real thorn in the side for optical astronomers and radio astronomers. If that's not enough, and it's slightly hard to imagine why, satellites orbiting in Earth's low orbit is sort of a problem. Let's take, for example, the Very Large Telescope. It's very important in detecting the quasar from the first article, and if these telescopes are heavily affected by radio transmissions, they won't be able to scan the sky for objects like the one we discussed. It makes it really difficult. And really, the effectiveness of such telescopes would be diminished, and that's probably as simply as you can put it. Although I should mention that this example that we have, the Very Large Telescope, is one that's only moderately effective because it's somewhere out in Chile where there's less radio pollution, I guess you could call it. And if you were to, say, take it from the perspective of an amateur radio astronomer in the United States, life would be a lot harder for those people because radio emissions are quite abundant in the United States, except for West Virginia, which has a radio quiet zone. So, yeah, in general, satellites creating strong radio signals and trails in visual wavelengths just messes up observations for all of us on the ground. The good news is that this issue has come up recently in the UN Committee on the Peaceful Uses of Outer Space, so it's come to their attention, and they'll be hearing about it and taking up this issue. They're going to be addressing concerns about how satellite constellations can disrupt Earth-based astronomy, specifically reflected sunlight from the satellites that can create streaks in optical and infrared images. So maybe less of the radio stuff because, actually I don't even know why, but at least they're taking up an issue with satellites being in low orbit. So the goal here for astronomers is really just to get a decision from the committee that will initiate national laws and regulations over the interference of satellites. And that's pretty much the bigger picture. Obviously, the UN committee is not looking at like all the different ways that satellites are affecting Earth-based astronomy, but the fact that they're taking it up sort of goes towards this bigger picture goal for astronomers. And that's good news. There's some downside to it, though. The process is that the decision will go forward in terms of action only if there's a unanimous decision from all 103 countries who are members of the committee. So, yeah, it might not go far, even if there's just like one or two countries that are not on board for some reason. So, this process might not work out as well as we wanted to, probably as well as the Articles of Confederation, if we want to be realistic. But the fact that the issue is being addressed after, I think it was nearly a decade, is still a win. And yeah, I wanted to discuss that because we can't always just spend time talking about like what's new, what's popping in astronomy, and not address some of the issues that we face in it. I don't know if I'll ever have the time to address sort of diversity in astronomy and how that affects things, but there are several issues in astronomy currently that we should pay attention to, and I wanted to make space on this episode for that and not just like always be like, oh my god, huge quasar. So yeah, that's pretty much what I got for the third article and our episode today. Hopefully I was clear on the microquasar stuff. It was a very brief but detailed explanation. I mean, the numbers really speak for themselves when it comes to our huge and luminous quasar that we talked about in the first article. So yeah, if you have any questions, comments, feedback, throw them in the comment section for the YouTube video. If you're on Spotify, I'm sure there's a Q&A there that will allow you to express your thoughts on this episode. And yeah, if you enjoyed the episode and you're new here, make sure you are subscribed. And I don't usually say this, but because I've realized recently that the returning viewer rate is really low, if you want to see these episodes more frequently in your notifications inbox, then make sure to click on that bell icon and select all for notifications so that you don't miss out on some of these episodes, because yeah, YouTube's just not good at recommending my content to returning viewers. So yeah, if you're on Spotify and you enjoyed the episode, then obviously leave a follow on Spotify and you'll be getting that in your notification inbox immediately or automatically. So yeah, that's all I gotta say. I don't know, quite a bit of digressing in this episode, so I'm gonna cut it off right there and see you all next week for the next episode. Peace.